All right, let's talk about data hazards and forwarding for the MIPS CPU with a simple 5-stage pipeline. These slides, I should mention, I got from Don Fusel. I don't actually know, but they're at UT Austin, and their slides are actually very good. They're the best I've found online from my extensive Googling. So here's some code that has some data hazards in it that can be resolved with forwarding. And then here is our cycle diagram, and you can kind of see what's happening. We got an R-type instruction, subtract. We want to write back into register 2, but then we're immediately trying to use register 2 in the next cycle. Now the write back doesn't happen until a couple cycles later, so we have this edge going back in time. That's not going to work. But if you think about it, the ALU actually produces the value, writes it to this temporary register. Well, if only we could take it from that temporary register and make it one of the inputs here to the ALU in the next cycle. Similarly, this subtract instruction wants to write into register 2. Well, here we have another R-type OR instruction which needs register 2. Well, remember, R-type instructions don't use the data memory, so they just pass this value right along. But again, we don't write back until here. We're trying to use the value again down here. We'd like to make another forward here. So we see we can forward from the EX to MEM stage, that's here, or from the MEM to write back stage, that's here. So we can forward values from this stage to the ALU, or from this stage to the ALU. We can actually make either forward. And so the question is, well, what does the circuitry have to look like to do that? So first we need to know the destination register, and we need to know the source registers. So if the destination register for the EX MEM phase is equal to either of the source registers from the decode to execute phase, well then we want to forward the ALU result from the EX MEM phase as an input to the ALU. Similarly, if the destination register for the MEM write back phase is equal to either of the source registers for the decode execute phase, that's also a forward situation. This and this, these first two pieces here, these correspond to this situation, so forward from the EX MEM phase to the ALU. This is forward from the MEM write back phase to the ALU. Both of these are examples of forwarding. And both of them are forwarding because if you look at these inputs to the ALU, the input register numbers, they're equivalent to the register that is in the future going to be written back but hasn't been written back yet. So I should mention one other thing. You only want to do forwarding if the register destination is not the 0 register. The reason being we're going to use the 0 register as the register we write to for no-ops, and we need to be able to allow no-ops. We don't want to do forwarding if we detect anything about the 0 register, so we just want to say, hey, look, if it's the 0 register, I'm not going to worry about it because we're not going to write back to the 0 register anyway. Now here's what the logic for this is going to look like. This isn't the full logic, but this gives you kind of a flavor of what's going on. First we have the destination register for the EX MEM phase. That's one input to the forwarding unit. Now a couple of other inputs are the source and RS and RT, the two source register numbers coming from the ID to execute phase. So here for the ALU, if we see that some of the inputs here are supposed to be registers, values that haven't been written back yet, and we know that by saying, well, look at this, the EX MEM register RD is equal to one of these, well that means we need to forward. What will we forward in that case? Well, we'd forward the thing that the ALU just produced. That comes up here, and that's possible, this is 0, 1, 2, that's input 2 to the multiplexers. And so these control signals here, if they see, hey look, this register number is equal to one of these, one or both of these input register numbers. If that's the case, well then use the value that the ALU just produced in the last cycle. Make that the input. Don't use the value we loaded from registers. That's stale data. That's data that hasn't been updated yet. Similarly, this register number here, this is the register destination for the write back, the MEM to write back phase. Well, if that equals either of these, then we take this value, in other words, which could be either something produced by the ALU or the data memory. We actually don't know. It depends on the control signal, but whatever one of those values it is, that is going to be input 1 to these two multiplexers. And so if we see that that register number is equal to either of the source register numbers, well then we set these control signals accordingly. So that gives us the basic idea of forwarding. Now, of course, there's a few other considerations. The number one consideration being all of this is only true if we're writing the registers. If we're not writing the registers, then don't do any forwarding. And so here's just a little bit more on what that logic would look like kind of in pseudocode and what the numbers are for the different forwarding to, register A, register B. Consider this sequence. So in this sequence, both hazards occur, right? Because here we're adding register 1 and 2, putting it in register 1. So this next instruction, well, we need to forward to here, but then this instruction, this is also forwarding to here, and then this is also forwarding to here as well. So if this happens, we want to use the most recent value. We don't want to use the older value, right? Because we wouldn't want to forward from here down to here. We would only want to forward from here down to here. Because this sort of add's been done, then we want to do the add again. So only forward if the hazard condition for, only forward mem if the execute phase isn't true. So that just makes sure that we only forward the most recent condition. It occurs to me that I think I got this wrong in my circuit. I'll have to fix that and test this example. But it's an important consideration. And so here's just some more logic of what this would look like. And then here's the full diagram. And so you can see the forwarding unit, well, it's got register RS and RT. Those are two of the inputs. And then it's got the register RD. Now I should note, the destination register, you might be looking at this and saying, Spacco, what the hell? The destination register, sometimes it's RD for an R-type, but for I-type instructions, the destination register is RT. Well, actually, we've already figured out what it is. So if you look at this, this is register RT and RD. Well, those hit a multiplexer. This is not shown here, but that multiplexer has a control signal, which tells it one of these values. So only one of them is in practice going to be the destination register, and that's the one that we're going to compare, right? Because at this point, we actually don't care whether it was RT or whether it was RD. We just care that whatever register we're writing to in the EX to mem phase matches one of the source registers here so that we know that this value needs to get forwarded to one of these inputs. That's all we need to know. Same thing over here. Now, one other important piece of information. So this is one of the inputs to this write back register is reg write. Are we writing the registers? That's one of the inputs. We have to know, are we writing registers for the instruction that's currently in the EX mem phase? And similarly, are we writing registers for the instruction that's currently in the mem to write back phase? So in order to check if this matches up with these two things, that's got to be true. In order to check if this matches up with these two things, that's got to be true. And all we're doing is setting control signals to multiplexers to let us know whether we should forward. Now, there are situations where we can't forward. So here's a situation. We've got a load instruction. It's loading from memory, putting the result in register 2. And then we're trying to use, in the very next instruction, register 2 as one of the inputs. Well, forwarding, or at least forwarding alone, doesn't help us here, because we're loading a value from memory that we also want to be the input to the ALU. These are happening in parallel, so there's no way forwarding. This forwarding still goes back in time. It's within the same instruction, but it's still going back in time because the memory's not very fast, but the ALU is also not very fast. So there's no way to have these happen at the same time, but have the output to one be the input to the other. This is a situation where we actually need to see that this is about to happen. In other words, that the destination register that we're writing to in this load instruction is the same as one of the inputs, RS or RT, in the next instruction. We have to see that and stall the pipeline. Oops. Oh, God, I jumped ahead. Here we go. So here's just some logic, and here's what we'll do. This is easier to figure out with diagrams. Here's what happens. So we're loading into register 2. We've loaded the next instruction. We've loaded its registers. And then at this point, we realize, uh-oh, the value that we just loaded into register 2 is also supposed to be one of the inputs here to the ALU. Well, this value might not be finished loading yet. We have to stall the pipeline. This is called stalling. Sometimes it's called bubbling. You create a bubble. We call it a bubble because what you do is all of a sudden at this moment when you detect, darn it, I'm trying to use one of the inputs to the ALU that I'm still in the process of loading from memory, we basically set all the control lines that we have access to 0, which effectively makes the rest of this a no-op. So we've detected that there's a problem, we've stalled the pipeline by making the rest of the instruction a no-op. We don't write the program counter with PC plus 4, we go back to just regular PC, which means we load this instruction again. Well, now we've basically stalled it for one cycle. When we load the instruction again, 2 is now ready. It's now legitimate to be forwarded because we've finished loading it and we can forward it to the ALU to be used in the next cycle. But in order for that to work, we either have to have another instruction in here or we need to detect that we're about to have a problem and stall the pipeline by making the rest of this a no-op and then reloading and restarting the instruction. So that's called stalling. And let me jump through. Here's what the circuit diagram for that looks like. Basically, if we know that there's a mem read, what we need to look at, this is sort of a little hard to see with all these lines here. If we track this back, we see that it's destination register RT. Why RT rather than RD? Why is it always RT? Well, load word instructions, the destination register is always RT. There's only one load word instruction. There's only one way in MIPS to get things out of memory and get them into a register. So we just check this register up here, and then we've got the rest of the instruction. This is RS and RT, the source registers for the next part of the instruction. So we're checking, well, are the inputs to the ALU, the source registers, are either of them equivalent to the data value that we just read and put into RT? And are we reading memory? If all those things are true, guess what? We need to stall the pipeline. Well, how do we stall the pipeline? Well, that's pretty easy. We tell this bank of registers here, guess what? Don't write this cycle. So we're going to tell these registers, don't write. What that means is whatever instruction we loaded, don't load the next one, just reload that same instruction. We're also going to tell the program counter, for this cycle, don't write PC plus 4. What that means is just reload the next instruction we were at. Now, this multiplexer here, you can see it's got a bunch of control signals or 0. If the hazard detection unit sees that there's a hazard, in other words, if it sees that the destination of a load, right, because memread is set and RT matches one of these source registers, so the destination of a load is the same as something we're trying to load, it's going to say, make the rest of this a no-op. This is a multiplexer where one input is all the control signals, that's what we normally do. The other input is just all zeros. So we set everything here to 0. Don't write back, don't read or write memory, we don't care what you do with the ALU, just make it a no-op. We're just going to say, screw it, make this a no-op, don't do anything. Stalls actually reduce performance, but they're actually required to make things work. The compiler, if it knows about this with stalls, it can actually try to rearrange the code. It can't guarantee it'll always rearrange the code, but it can try to rearrange the code to reduce the number of stalls. And I think what we actually have next are branch hazards, which we're not really going to get into. So that's all I've got. We're going to go ahead and implement this in Logisim.